Curvy coordinate geometry, slightly different to what we were talking about last week. So if you haven't got here yet, don't worry, never fear, it's coming. Okay, if you're already here, brilliant, it's perfect timing. And if you're ahead, great revision. So what we're going to do is the same thing as we've been doing previously. This lesson is going to focus on the theory, and then next week we're going to focus on past paper questions. So working through what we talked about today and actually using it in past papers. So the big thing to start with, sorry, let me get my list of people out. One disappeared when I got my whiteboard out. Okie dokie. So where were we? Sketching. Okay. You've come across the concept of mini sketches already, hopefully, when you've done your quadratic inequalities. Okay, mini sketches are just little bits of understanding. It's a scribble for us to help figure out what the question is doing. When we're talking about sketching here, we're talking about sketching a little bit more nicely. Okay, we're sketching now for our examiner, but we are not plotting like we did at IG. There is no graph paper involved in AS. Okay, there'll just be a blank space in your paper and it's there for you to just draw in a graph. So what do we need to do? We don't need to measure and draw a whole lot of axes. There are important features that we are going to consider. And there are general shapes that we're going to bear in mind. So, important features. You should be familiar with these, I'm hoping. Your y-intercept. This is a revision of IG work. Your x-intercept. And then we're going to add your stationary points. So, where did these come from? The y-intercept, this is when x equals 0. It's your constant term. So generally you don't even have to calculate for this one. It's there when you look at your function. Your x-intercept, y equals 0. Easiest way to get this is to factorize. Stationary points. Okay, I know some of you are further on in the course, so you've done calculus, you've done differentiation, you know how to get a stationary point. So once you get there, then you would be expected to have proper indication of your stationary points. If you haven't yet got calculus, you're just aiming for a ballpark. It goes up, it goes down. Okay, you're not aiming for where exactly is that stationary point. Once you've done calculus, yes, it goes in. Right, so that's your important features. Okay, and we're going to combine that with a general shape understanding. Okay, so x squared, x cubed, x to the 4 are your major ones. But what's really cool is that there's a general pattern running through all of them. Okay, so before we move into what are those general shapes, I just want to do a little bit of more basics, because these are the things that some people rather forget. You notice I've changed to gray, right? Because this is pencil. Pencil is gray. And you use a pencil to draw your axes with a ruler, which I don't have. Actually, wait, hold on. Haha! Okay. Zoom is very funky. So let's just get rid of this one, because in Zoom, I think, magic. Okay, there's my ruler. There's my axes, drawn with a ruler in pencil. Right, I like this. Then, let's say we have a curve. Okay, curve is also drawn in pencil. Let's say our wonky wobbly curve looks like this for now. Okay, he was drawn in pencil, right? But we don't write in pencil, we write in pen, preferably back pen. So, y-axis, x-axis. And we don't go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 all along our axis, because we're not drawing these things to scale. We're not drawing them accurately. So the only thing we would label is, let's say this is 5 and this is 4. And we put a 0 in just for neatness. Okay, that's part of drawing our axes. So, oops, we need our pencil back again. You are going to draw in pencil. You're going to use a ruler for axes. You're going to write in pen. You're going to label your axes, and you're going to label important points. Only. Okay, we don't want lots of numbers. We just want a clear sketch that indicates exactly where everything is. Okay, right. So let us talk now about general shapes. Understanding what our curve should look like when we actually come to draw it. So, a little bit more detail on let's have him here for interest's sake. Let us have x to the 1. Okay, so we wouldn't normally put that 1. Okay, he's normally just our x, and he is linear. Okay, he's not actually a curve, but he's interesting because of what's going to happen next. So he can go up, or he can go down, depending on gradient, positive gradient, negative gradient. Okay, we're happy with this. So this is plus x, this is minus x. Okay. If we then make a little bit more space so I can see what's going on here, do this. Let's say we have x squared, okay, because this is another one that I'm hoping you're familiar with. Here's your quadratic. Funnily enough, he also has different patterns depending on whether he's plus ax squared or minus ax squared. So positive people are happy people. Plus x squared is a smiley face. Minus x squared is a sad face. So don't be negative, be positive. Okay, right. So here, let's just add one more thing. We're talking about x to the n here. And what we've got here on our linear side is that n is odd. What we've got here on the quadratic side is n is even. So if you just learn your linear and your quadratic, which you should already even know, you can actually figure out everybody else. Because this is our general pattern. Smiley face and a sad face and a line up with a line down. If we look at x cubed, so our cubic, guess what happens if we go plus x cubed? We go up, we blip, and we go up. If we have minus x cubed, we go down. Whoa, we have a very weird blip. We blip, and we have minus x cubed. So we have that overall up and down exactly as for our linear. If we have x to the 4, so we have our quartic graph. Well, we have a smiley face with blips. So, like that is plus x to the 4. Sad face with blips, now we're getting to draw teeth, minus x to the 4. Okay, so that same general pattern is happening over and over again. How many blips do we get in our line? That is related to our n. So the relationship is for x to the n, maximum number of stationary points is n minus 1. So we can see that's right. X to the, well, what n is 1, 1 minus 1 is none, we have no stationary points. 2 minus 1 is 1, we have 1 stationary point. 3 minus 1 is 2. Whoops, there's 2 stationary points, 2 stationary points. And 4 minus 1 is 3. 1, 2, 3 stationary points. 1, 2, 3 stationary points. So the thing is that as we go through this, this is something to bear in mind that it's the maximum number of stationary points. You are often going to get a cubic with less. Okay, they often like to draw that where you have your cubic that sort of squiggles. It's more of a point of inflection than actual 2 stationary points. But these are the things to bear in mind for your classics. Okay, so one other one, which is sort of done as an aside in your textbook, but comes in very helpful when it comes into understanding domain and range for some of your more fun functions. So let's just talk now for a bit. We've got the time, brilliant. I'm doing better today. This week is going better with time management. Okay, so let us talk general shapes for 1 over x to the n. Okay, so some of you were in the Q&A a few weeks back where there was a 1 over x to the n graph that was giving us headaches. Okay, so back to basics. Okay, we're going to do the same thing. Okay, let's look at when n, whoa, n is odd against n is even. Okay, so what are we going to do? We're going to have 2 very different curves. Okay, these are very dodgy sketches because we're not doing the whole pencil and rulers and all of that. I must remember now that I can do arrows nicely. Okay, so if n is odd, 1 over x squared to cubed, oh golly, 1 over x himself, I've drawn these back to front. Okay, if n is odd, 1 over x, 1 over x cubed, 1 over x to 5. Then we have this one. And our graph is going to sit in this quadrant here and this quadrant here. Okay, if n is even, then our graph is going to sit in this quadrant here and this quadrant here. So now you can see directly the link to, if you were in the Q&A session that time, that we can see directly how we have these asymptotes, and that's what's important here. Okay, we're not going to cross these axes if we just have 1 plus x to the n. Okay, so this one comes with beware of transformations. Okay, 1 over x to the n plus 4, for example. And let's say that's odd. What it's going to do is it's going to shift the graph up 4. You could get then an axis intersection. Okay, so transformations can lead to axes intersections. So, and this is part of the reason why we don't go into such great detail with this. We're not learning this in our coordinate geometry chapter. It's something that we're going to be aware of, and it's going to tie into other things. So it's one of those sort of pieces of knowledge that grows with your development and your understanding as you go through the course. Talking about these transformations is something we actually do when we learn about trig graphs, because trig functions are also functions. They also work just as reliably as all of these other curves that we're drawing now. Okay, so just bear this in mind if you're still at the beginning of the course. If you're later on in the course, it'll make a lot more sense to you and you'll sort of start to see the application of it. Okie dokie. Right. So we now have a good idea of what sketching is and what general shapes are. So we've got this basic ability to work with a curve. So let us have a look now at intersections between line and curves. The last element of this story. Okay, so if you are ever solving these simultaneously, you've got to keep your life easy. We want to do linear into curve. We don't want to be trying to do all weird roots of some funky curve equation. Okay, linear into curve, keep it simple. Do not make your life uglier than it needs to be with your algebra. Okay, so got the basics down. What we want to talk about today is the number of intersections, because there's some funky things coming in here. So if we consider the number of intersections, okay, we could have different situations. We could have, okay, let's get some little mini sketches going for this. Let us consider, we don't need those, we're going to keep it nice. So, quadratic, 3 happy quadratics, and a basic cubic. Okay, now let's give ourselves a line. So we could have a line that goes like this. We could have a line that goes like this. And we could have a line that goes like this. Okay, same sort of story here. We could have a line that goes like this. We could have a line that goes like this. Or we could have a line that goes like this. Okay, and we've gotten ourselves 3 different situations. In this first situation, we have all intersections distinct. Here, we have a shared intersection. Here, we have a shared intersection and a distinct. So, all or some intersections shared. And this last situation, we have no intersections. So if you have done the discriminant, bells should be screaming in your head. Oh, this sounds familiar. Whoopsie daisy. Oh gosh, I just pressed on something and then I lost my share screen. Okay, it's back. Right. Okay, so we were screaming about this looking familiar. And what is wonderfully brilliant is that he should sound familiar. We just changed the word solutions for intersections, and we can use the discriminant. Told you he'd be a good friend. So, 2 distinct intersections, b squared minus 4ac greater than 0. 1 shared intersection, so a repeated intersection, a tangent to the curve, b squared minus 4ac equals 0, and there's your word, tangent. And no intersections, same as no roots, no solutions, b squared minus 4ac is less than 0. So all we did was we changed one little word in that discriminant phrase, and it works so beautifully. So we can use that discriminant. We can see, do we have 2 intersections that are distinct? Do we have 2 intersections that are shared? Are we looking at a relationship tangent to curve, or no intersection at all? So remember that if you want to do this, you can't just look at your equation of your curves. Okay, you've got to use a discriminant on simultaneous equations first. Okay, so you do your simultaneous first, so that you have one equation that represents, if you can spell represents, quadratic, okay, spelling has gone out the window, and line together. Then you can do your discriminant. work with it depending on what information you've got. So we'll do some lovely questions next week that show you how this works. So if you're here today, you're going to have to be here next week. Okay, when it comes to your cubic, yes, we have the same set of relationships, but we do not have that same funky friend in the discriminant. Unfortunately, the discriminant only works for quadratics. For a cubic, you're going to have to turn your brain cells on. So, you would have to look at your curve and look at your line and then figure out, let's go this one. Oh, hold on, sorry. We want to just do these ones. Okay, so look at your curve, look at your line, and figure out the solution. And that is where your sketching is such a powerful asset. So here, you are going to have to sketch and think. Okay, so if my line was here, would it intersect or not? If my line was there, would it intersect or not? Where would I need to put my line in order to get so many intersections? So it's a real understanding of your curve and a real understanding of your line. And why, again, I say that sketching is so important. All right, so then I have actually finished slightly early, which is wonderful. Have we got any questions, seeing as we have time to play with? Or do I need to think of something to fill the last 5 minutes? I shall give you some typing time. Okay, so either everybody is typing enormously long questions or no one is typing at all. So we must substitute. Simultaneous equations, line and curve, yes. You are going to end up often solving by substitution because it is one of those things where elimination is not going to work when you've got different powers. So different versions of substitution, you can have y equals linear, y equals curve, and then you can say linear equals curve. Or it could be a case of you're rearranging your linear and putting it into your curve in different points, depending on what you've got. Generally, often you're going to find that it's y equals linear, y equals curve, and then you just say linear equals curve, and you are happy with everything. Okay, so we have another one, all good. Have we got any other questions or essays coming through? Okay, so then let us save this and yes, okay. So let us very quickly then substitute linear into the curve for one equation before using the discriminant. Yeah, so let's say we had y equals, oh gosh, now you're pushing, x squared plus 3x minus 4. Okay, and we have y equals x plus 2. Oh, no, wait, we should be a little bit clever. We should say, because they like doing this. Whoopsie. There. Y equals x squared plus 3x plus k. And then they say something like find values of k for which line is a tangent to curve. Okay, so that's your classic sort of basic question when it comes to this whole using the discriminant. So in order to do line is a tangent to the curve, we first need to represent this in one equation. So we would say, put them together, x plus 2 equals x squared plus 3x minus k. We could even give them here for a combined equation. So letting our examiner know what our thought process is. Bring everybody to one side. X squared plus 2x minus k minus 2. And now we've got a quadratic. And we can use a discriminant on this. So it's another reminder of what's A, B, and C. The yellow is too bright, I remember. So there's your A, there's your B, and there's your C. So let's see how well my numbers worked. Line is a tangent. That means that b squared minus 4ac equals 0. We have a repeated root. So got a combined equation. We now need 4 values of k. In fact, we're a little bit dodgy here because we're making questions up. This is going to be a single value of k because b squared minus 4ac equals 0. So b squared is 2 squared minus 4 times a times c. And it equals 0. So 4 plus 4k plus 2 times 4 is 8 equals 0. Just check that I've done that right. So 4k plus 12 equals 0. This is magic. So 4k equals minus 12. Let's play safe and go slowly. K equals minus 3. So if we had x squared plus 3x minus minus 3, so plus 3, then this line would be a tangent to this curve. Okay, so that's where we say in pink from the previous slide that first we have to do our simultaneous equations, and then second we would use our discriminant for the value of k. So does that make sense? Is that question sorted? Have we got smiles and nods to end the session?